For the next few moments, nothing needs to be solved quickly. The questions in this story are larger than any one night, and they will still be here tomorrow. Allow the sounds around you to become part of the background. Let your breathing continue without effort, while we travel farther than any spacecraft has gone. Our ship is imaginary, quiet, and warm. Its wide windows allow us to look into darkness, without treating darkness as a threat. Tonight's question sounds simple. If we traveled to the end of the universe, and looked beyond it, what would we see? Would there be empty space, another universe, a place with different laws of nature, or beings so advanced that human language has no useful name for them? Before we leave, we need 3 labels. What science has established through observation and testing, we will call knowledge. What is supported by a physical theory, but has not been confirmed, we will call a hypothesis. What we add only to explore an idea, we will call imagination. All 3 can share one story, as long as we do not confuse a beautiful idea with evidence. The ship rises above Earth. Cities become amber threads. White clouds cover the oceans, and the atmosphere narrows into a blue ribbon around a small world. Every human question about the universe began beneath that ribbon. Astronomers, mathematicians, children looking through bedroom windows, and every person who has ever wondered whether we are alone, have all stood on the same planet. From far away, Earth has no national borders, and no sign that one human idea matters more than another. It is a small planet orbiting an ordinary star inside one galaxy among an enormous number of galaxies. We pass the Moon, Mars, Jupiter, and the faint outer regions of the solar system. The Sun becomes one point among many. Nothing has happened to it. It is simply too small and distant to remain the center of our map. We cross the imagined Oort cloud, and enter the wider sea of the Milky Way. Dense starlight surrounds the galactic center, but our path rises away from the disk, until the Milky Way becomes a bright spiral behind us. Our galaxy belongs to the local group with Andromeda, Triangulum, and many smaller galaxies. From farther away, these systems become part of structures held together and shaped by gravity. On the largest scales, galaxies are not sprinkled evenly through space. They form filaments, walls, and luminous knots around vast empty regions. This pattern is called the cosmic web. The web does not hang inside a larger room. It is the distribution of matter within space itself, built by gravity over billions of years. As the ship continues, kilometers become useless. We measure distance in light years, the distance light travels in 1 year. Light is fast enough to circle Earth several times in a second. Yet the universe is so large that light can spend billions of years crossing it. When we observe a distant galaxy, we do not see it as it is now. We see the light that finally reached us. A telescope is therefore also a time machine. Looking farther into space means looking deeper into the past. The universe is about 13.8 billion years old. That does not mean the observable universe has a present radius of only 13.8 billion light-years. While the light traveled, space expanded. The place that emitted it is now much farther away than it was when the journey began. For that reason, the present radius of the observable universe is roughly 46 billion light-years. This does not require an object to move through local space faster than light. It is the large-scale distance defined by expanding space-time that changes. Our ship now approaches what people often call the edge of the observable universe. The word edge suggests a cliff, a wall, or the skin of a ball. The cosmic edge is none of those things. It is a horizon, a boundary between regions whose information has had time to reach us, and regions whose information has not. Stand in the middle of an ocean, and the horizon forms a circle around you. Sail toward it, and it moves with you. Another observer on another ship has a different horizon. The cosmic horizon works in a related way. It describes the limits of what a particular observer can receive, not a place where reality must stop. If a galaxy lies beyond our horizon, an observer inside that galaxy may have an observable universe of their own. Their visible region could overlap ours, while also including places from which no signal will ever reach Earth. So the most careful answer to the question, what is beyond the observable universe, may be much less dramatic than a movie. There may simply be more galaxies, stars, black holes, gas, dark matter, and space continuing beyond what we can see. There is no evidence for a wall carrying a sign that says the universe ends here. What stops at our horizon is not necessarily space. It is the information available to us within cosmic history. Farther back in time, we encounter the cosmic microwave background, the oldest light we can observe directly. It was released when the universe was about 380,000 years old. Before then, matter was so hot and ionized that light scattered repeatedly instead of traveling freely. As the universe cooled, electrons joined nuclei to form atoms. Space became transparent, and the ancient light began the journey that ends in our instruments today. The microwave background is not the outer wall of the cosmos. It is more like a fog that became clear. There is an earlier history behind it, but ordinary light cannot show that history to us directly. Scientists reconstruct the earlier universe, using the pattern of tiny variations in the background, the distribution of galaxies, particle physics, and other testable clues. The evidence describes an early universe that was hotter, denser, and expanding. The Big Bang was not an explosion from one point into a pre-existing empty room. It describes the expansion and evolution of space from an early hot state. Every region we observe was closer to every other region in the past. There is no location, in today's universe, that can be pointed to as the place where the explosion happened. This matters when we ask what the universe expands into. Our intuition imagines a balloon inflating inside a room. Cosmology does not require the external room. Distances within space can change without space being embedded in another ordinary space that we can visit. Imagine a two-dimensional creature, living only on the surface of a sphere. It can move forward, turn, and measure distances across the surface. The surface can be finite without having an edge. If the creature walks in one direction long enough, it may eventually return to its starting point, without ever meeting a boundary. The sphere exists in 3 dimensions in our example, but the creature's internal geometry can be described without giving it access to that 3rd direction. Our 3-dimensional space could also have a global shape that is finite yet unbounded. Or it could be infinite. Current observations show that space is very close to geometrically flat on large scales, but they do not prove that the entire universe is infinite. A region can look flat if the curvature scale is much larger than the region we can observe, just as a small field looks flat on the surface of Earth. The total universe may be vastly larger than the observable part. It may even be infinite. We do not yet know. Geometry and topology are related, but they are not the same question. Geometry describes local properties such as curvature. Topology describes how the whole space may be connected. A flat sheet can be infinite, but a flat surface can also be wrapped so that crossing one boundary returns from another direction, like the logic of an old video game screen. In 3 dimensions, there are more complicated possibilities. Space could be multiply-connected, allowing light to reach us along more than one path. If the observable region were large enough compared with the full topology, astronomers might see repeated patterns of galaxies, or matching circles in the cosmic microwave background. Searches have constrained many simple versions of these models. No convincing repeated pattern has established a small, wrapped universe. That result tells us that if space has such a topology, its fundamental scale is probably larger than the region those observations can test. It does not tell us what an imaginary observer would see from outside, because an outside is not automatically part of the model. The phrase outside the universe may be grammatically easy, while physically undefined. North of the North Pole sounds like a direction, until the geometry of Earth is understood. In a similar way, beyond all space may not name a location at all. Yet the question remains useful, because it exposes which assumptions come from physics, and which come from the pictures in our minds. This is the point where established observation begins to hand the story to hypotheses. One group of ideas grows from cosmic inflation. Inflation proposes that the very early universe experienced an extremely rapid expansion. It helps explain why distant regions have similar properties, and why space appears nearly flat. Several inflationary models fit important observations, but the underlying mechanism has not been directly identified. In some versions, inflation ends in one region while continuing in others. The result is sometimes called eternal inflation, many bubble-like universes, forming within a larger inflating structure. Each bubble could possess a hot beginning like ours. Some models allow different low-energy physical properties in different bubbles. No neighboring bubble universe has been confirmed. If eternal inflation occurs, most other bubbles would remain permanently beyond causal contact. Their light could never cross the inflating region between us. That creates a difficult problem for science. A model may generate many universes, but predictions require a meaningful way to compare how often different outcomes occur. In an eternally growing structure, both rare and common events may happen an infinite number of times. Defining probabilities then depends on a measure, and different measures can produce different answers. Some physicists connect the multiverse with the apparent fine-tuning of physical constants. If many regions have different effective constants, observers would naturally appear only where long-lived stars, stable chemistry, and complex structures are possible. This is an anthropic form of reasoning. It may help explain selection effects, but it can also become too flexible if it is not joined to testable predictions. The strongest scientific version of a multiverse would not merely say that anything can happen somewhere. It would arise from a theory that also makes precise, successful predictions about observations inside our universe. Inflation itself can be tested through features of the cosmic microwave background and the distribution of structure. Particular versions predict different patterns. Future measurements of primordial gravitational waves or other early universe signals could eliminate many models or strengthen a narrower family. Even then, evidence for inflation would not automatically confirm every possible multiverse built from it. Researchers have searched for possible traces, such as unusual patterns that a collision might leave in the cosmic microwave background. No accepted detection has emerged. The idea belongs to theoretical physics, not to a catalog of discovered worlds. Another use of the word multiverse comes from quantum mechanics. Quantum theory predicts probabilities for measurement outcomes with extraordinary accuracy. In the many worlds interpretation, the mathematical state evolves without a unique collapse, and different outcomes belong to effectively separate branches. This is an interpretation of the theory, not an experimentally visited collection of alternate Earths. Other interpretations make the same tested predictions, without describing branching worlds in the same way. At present, ordinary quantum experiments do not give us a simple device that chooses between these philosophical pictures. A third possibility appears in theories with extra dimensions. Human experience gives us 3 spatial directions, and 1 direction of time. Some mathematical frameworks include additional spatial dimensions that are hidden, compact, or inaccessible at familiar energies. In certain models, Our observable universe behaves like a three-dimensional surface, sometimes called a brain, inside a higher dimensional setting. Another brain could exist without being reachable by ordinary light and matter. Gravity might interact with the larger geometry in ways that other forces do not. These ideas have motivated searches at particle colliders and in tests of gravity at short distances. No extra spatial dimension has been confirmed. The mathematics may be elegant and useful, but elegance alone is not evidence that nature selected the model. Our imaginary ship cannot simply turn toward an extra dimension, as if it were a hidden road behind Jupiter. If such a direction exists, accessing it may require energies or conditions far beyond anything a spacecraft could produce. Now we turn from universes to life. Even if the cosmos outside our horizon is ordinary, it may contain an extraordinary number of worlds. Astronomers have confirmed thousands of planets around other stars, and the number continues to grow. Planets appear common. Small rocky worlds, giant planets, tightly packed systems, and planets orbiting two stars have all been found. But a planet is not the same as life, and life is not the same as intelligence. We have no confirmed detection of extraterrestrial life. Scientists search for biosignatures, atmospheric gases, surface features, or chemical patterns that might be difficult to maintain without biology. Every candidate must be tested against non-living explanations. Geological and atmospheric processes can imitate signals that initially appear biological. The most responsible claim requires several independent clues that agree. Intelligent life introduces another set of possibilities called technosignatures. A technosignature is evidence of technology rather than simply biology. It could be a narrowband radio signal, a structured optical pulse, an unusual industrial chemical, waste heat, or a large artificial modification of a star system. No technosignature has been confirmed as extraterrestrial. Radio searches examine enormous combinations of frequency, sky position, bandwidth, repetition, and signal drift. A transmitter on a rotating and orbiting planet would not remain at one perfectly fixed frequency from our point of view. Its motion creates a changing Doppler shift that search algorithms must recognize. Optical searches look for pulses that are too brief, intense, or regular to resemble familiar astrophysical events. Infrared surveys can search for waste heat. Any civilization using energy must eventually release lower temperature energy unless it has discovered physics that overturns thermodynamics. The challenge is that nature also produces infrared excess. Dust around young stars, debris disks, and obscured galaxies can imitate the broad signature of engineering. Atmospheric technosignatures might include manufactured chemicals that are unlikely to accumulate through known geology or biology. Future telescopes may be able to study the atmospheres of nearby rocky planets in greater detail, but separating a technological signal from an unfamiliar natural process will demand caution. Artificial illumination on a planet's night side has also been discussed. At interstellar distances, such light would be extraordinarily faint compared with the host star. Megastructures could produce unusual transit patterns as they pass in front of a star. Irregular dimming attracts attention, but dust and fragments can create complex patterns without technology. The lesson is repeated across every method. An anomaly is the beginning of an investigation, not the announcement of an alien civilization. Independent instruments must confirm it. Local interference must be excluded. Natural explanations must be tested with the same seriousness as the exciting one. The search space is so large that our present effort has been compared with sampling a small amount of water from Earth's oceans, and concluding that the ocean contains no fish. The comparison is imperfect, but its message is useful. A non-detection becomes meaningful only when we define exactly what signals, strengths, distances, and durations the survey could have found. The absence of a detection does not prove that no civilization exists. Our searches cover a tiny fraction of the possible frequencies, directions, signal types, and times. Earth has produced strong radio leakage for only a brief moment, compared with the age of the galaxy. Another civilization may communicate in a way we do not recognize, may transmit only rarely, or may have ended millions of years before our instruments were built. To imagine technological scale, astronomers often refer to the Kardashev scale. A Type 1 civilization uses energy comparable to that available on its planet. A Type 2 civilization uses energy comparable to the output of its star. A Type 3 civilization uses energy on the scale of an entire galaxy. Humanity is below Type 1 in this framework. A civilization near Type 2 might build a swarm of collectors around its star. Popular culture often calls the complete idea a Dyson sphere, although a swarm of many orbiting structures is more physically plausible than one rigid shell. Such a system would absorb visible starlight and release energy as heat, creating an unusual infrared signature. Astronomers have searched for stars and galaxies with suspicious energy distributions. Natural dust and ordinary astrophysical processes explain the known candidates so far. A civilization far beyond us may not remain biological in the form we recognize. It could move its minds into machines, redesign its bodies for different environments, or live primarily in artificial worlds. Its communication might operate on timescales too fast or too slow for us to notice. What looks like a silent asteroid could contain computation. What looks like empty interstellar space could carry signals hidden below our sensitivity. This leads to the Fermi question. If advanced civilizations could arise and spread, why do we not see clear evidence? There is no single Fermi paradox solution. There is a long list of possibilities. Perhaps life begins rarely. Perhaps complex cells are rare. Perhaps intelligence often destroys itself before becoming interstellar. Perhaps travel between stars is much harder than optimistic calculations suggest. Perhaps advanced societies become efficient and quiet instead of covering the galaxy with obvious engineering. Perhaps we live early in the history of habitable environments. Or perhaps evidence is present, but we have not learned how to recognize it. The Great Filter is the name given to a step that very few evolutionary or technological histories manage to cross. The frightening uncertainty is whether that filter lies behind humanity or ahead of us. If the origin of life is almost impossible, then reaching intelligence may mean we have already crossed a rare barrier. If simple life is common but technological civilizations remain brief, the most dangerous barrier may still be waiting. There are also ideas such as the zoo hypothesis, in which advanced civilizations deliberately avoid contact with younger worlds. It is an interesting story, but it is difficult to test, and therefore should not be used to explain away every absence of evidence. A hypothesis that can fit any possible observation risks, predicting nothing. Now imagine an intelligence not merely more advanced than humanity, but separated from us by millions or billions of years of development. The difference might not resemble the distance between old and new technology. It might resemble the distance between a bacterium and a mathematician. Such beings could manipulate stars, create artificial habitats, or perform computations using entire planetary systems. If physics permits stable wormholes, controlled black holes, or engineering of space-time, they might understand them long before us. But every step in that sentence moves farther from evidence. We know that intelligence can create technology because humans do. We do not know that any civilization can survive long enough to reach cosmic engineering. Could something be above an entire universe? One idea is a universe created in a laboratory, perhaps through processes related to inflation or black hole physics. Another is the simulation hypothesis, which asks whether our experienced reality could be generated by computation in a larger reality. These ideas raise serious philosophical questions, but there is no accepted observation showing that our universe was built or simulated. Any proposed test must distinguish the idea from ordinary physical explanations. Otherwise, the claim becomes impossible to confirm or reject. It is tempting to call a sufficiently advanced creator a god. Science must be more precise. A powerful being inside a larger natural system would still be a physical entity, not automatically the answer to every metaphysical question. And if that being had creators, or lived inside another universe, the question would simply move one level higher. What lies beyond that level, and beyond the level beyond it? An infinite chain of explanations is possible in language. Nature is not required to make the chain accessible to us. Our ship has reached the farthest point that evidence allows. Ahead is not a wall, but uncertainty. Behind us are the observations we can trust. Expanding space, ancient background light, galaxies forming a cosmic web, and physical laws tested across enormous distances. Beside those observations are hypotheses, inflationary bubbles, hidden dimensions, quantum branches, and advanced civilizations. Beyond them is imagination, useful when it generates questions, but dangerous when it pretends to be a result. We turn the ship toward home. The cosmic web becomes brighter. Distant galaxies return to the windows, then the local group, then the spiral disk of the Milky Way. The sun separates from the surrounding stars. The outer solar system appears as a quiet family of cold worlds and small bodies. Neptune passes below us, followed by Uranus, Saturn, and Jupiter. Mars becomes a red point. Earth becomes a blue one. The atmosphere widens from a thin line into a sky. Nothing in the journey proved that a multiverse exists. Nothing proved that an alien civilization is waiting beyond our horizon. But the journey did reveal the true size of our uncertainty. We know enough to describe the observable universe with remarkable precision, and not enough to say that the observable universe is everything. We know that planets are common, and not whether life has begun on any of them. We know that human intelligence can ask questions about dimensions, horizons, and cosmic history, even while living on one small planet. Perhaps the most important possibility is not that a superior being is watching us. It is that reality may contain structures and histories larger than the categories our minds evolved to use. That possibility does not make evidence less important. It makes careful evidence more important than ever. Earth grows beneath the ship. Clouds move across the oceans. Cities glow along the night side, and the blue atmosphere holds every confirmed living thing we know. The largest question can rest here for now. There is no need to force an answer from the darkness. The universe is allowed to remain larger than tonight's understanding. Our ship becomes still above the planet, while the unanswered possibilities continue quietly beyond the window.